hand it over to Darice.
Thanks, Nick. Hello, everyone. Welcome to the Introduction to PySAM webinar. My goal today is to introduce PySAM, SAM's improved Python wrapper, a thin layer of code that translates a library's existing interface into a Pythonic interface. This webinar is targeted for experienced Python programmers who have some familiarity with Anaconda, Python packages, and SAM. You'll be able to tailor renewable energy system simulations from your Python scripts with better visibility, error reporting, and easy conversion between Python and the underlying SAM library. I'm Darice, a renewable energy system modeler here at NREL. During this webinar, we'll quickly demonstrate how to set up a utility-scale PV project. I just lost my connection. My internet just stopped. Oh, sorry about that. It's just a couple of technical difficulties. So we'll quickly demonstrate how to set up a utility-scale PV project in PySAM and PySAM, then focus on demonstrating how to get started with PySAM by going through installation, executing models, importing from SAM, and accessing compute modules. So Python users access the SSC algorithms through a wrapper called PySAM, which I will demonstrate quickly here. However, we recently released a new wrapper called PySAM, which adds more functionality in Python and is easier to use. The old PySAM wrapper is still bundled with the new PySAM wrapper. I'll create in SAM a PV watt single owner case. Then SAM's code generator, as Nick pointed out, can be used to get the Python script that will set up and run this PV watt single owner case. Currently, the Python code produced is for PySAM, but will be updated for PySAM in a future release. So I've made a folder for this webinar, so I'll save the files here. SAM exports a CSV containing the dispatch factors time series, the PySAM file, the SSC library and its header file, and a Python script with the same name as the case. Looking at that code, the function dataCreate in PySAM returns an SSC data table into which you'd insert key value pairs using the set functions such as dataSetString, dataSetNumber. To run PV watt simulation with that data, you create the appropriate module with module create and provide the data table to the module exec function. Once you've completed the simulation, you'd extract output values using the get functions. Then we'd insert key value pairs for the single owner simulation into the same data structure and then execute that. Finally, we can extract outputs and free the data. Running this script, we see the annual energy and the PPA price, among other results. Next, I'll show how to run the same simple case in PySAM. Default configurations are now accessible from PySAM. So I've written a simple script that performs the same simulation. So in this script, we start by importing the PV watts and single owner modules from PySAM. Then we will create default PV watts models and a default single owner model with default configurations from PV watts owner. Next, we'll set up the solar resource property in the location and resource group to be the resource .csv that I've included in this project folder here. Then we will execute PVWatts. After that, we will transfer the annual energy output from PVWatts into this generation property for the single owner model. We also have to set up the single owner model to not use lifetime mode. So we set system use lifetime output to be 0. Then we can execute the single owner model. Finally, we'll print the annual energy and the PPA price. So running this script, we see the annual energy and the PPA price is the same. Now that we've seen what PySAM looks like, we'll learn in the remainder of this webinar how to install PySAM, how to create, modify, and use all the renewable energy system models in SAM, how to import a technology and financial simulation from SAM, and finally, how to search for and access any of the functionality in SSC. The PySAM package and documentation is built from the PySAM repository here. The package is listed on PyPy and Anaconda Cloud. The documentation is found on Read the Docs. Everything we'll discuss here is documented in the Getting Started guide on the website. The requirement is 64-bit Python version 3.5 and above. No additional software is necessary. We support Linux, Mac, and Windows. So we're going to start with how to install PySAM. I'll demonstrate how to get it started with a new Anaconda environment. So first, we'll create and activate a new Conda environment with Python 3.7. So then I'll activate my new environment called Demo. Then there are two ways to download, either through Anaconda Cloud or the Python package index. We'll do the second method since it's easier, but info on downloading from the NREL channel on Anaconda Cloud is available online. Pip install NREL/-PySAM. And then pip list will show the list of installed packages. Note the name has NREL prefixed to distinguish it from other packages with similar names. You may notice that an additional package was downloaded as a dependency. This stubs package contains type annotations that help integrated development environments, or IDEs, analyze your code, and provide auto-suggestions. Then, of course, we'd like to explore and run some models. The list of models is available on the documentation page. Each model's under Available Models, Module Names and Descriptions. Each model's page provides information for the default configurations and the groups of variables. The model matching name in the SAM desktop is provided here. We'll use the PVWatts single owner case example to go through the new features of PySAM. We will set up auto-completion in PyCharm and IDE, access variables, and decipher error messages. To set up auto-completion in PyCharm, we'll start by creating a new project in the PySAM talk folder that I've prepared, and getting it set up with our newly created Anaconda environment. Not everyone uses PyCharm or an IDE, so this step is optional. So I'll create a new project in my PySAM folder, or PySAM talk folder. And then I'll point the existing interpreter to be the newly created demo environment. So I will click yes to use the existing sources in my project. Once I've gotten the interpreter set up, I'll configure it to run the demo script, which I've created for this webinar and which will be posted alongside it. So the demo script here will be using the correct interpreter. Now we should get auto suggestions for this PySAM package. So in the first line, again, I've imported the PV watts model. Now I'll create a new instance with the new function, which will return an empty PV watts model. Now as we explore this class, you'll see the group names pop up, such as system design and location and resource. Within each group are the SSE variables, whose type, label, options, units, and other information are available in the documentation. For those familiar with the GUI, the grouping of each model's variables usually corresponds with the tab on which the variables show up. So we can set these directly in the code by assigning floats, strings, dictionaries, tuples, and lists. But I'll switch to the Python console to better demonstrate. So again, I'll import the module and create an empty model. Now I'll want to set the azimuth property in the system design group, which I can do directly here. And we see that it's been set to 3. Another way to access model groups and variables is through the set attribute and get attribute functions. So set attribute can be used on the azimuth property attribute. Likewise, we can use get attribute. Bigger. The get attribute function can also be used on the model itself to get the groups. So here I can get the system design group and look at the azimuth. So the data can also be assigned or exported as a dictionary of variables. I'll create a dictionary called system design of all the system design variables that I want to set. Then I can use the assign method of the system design group. The export method of the group will produce a dictionary. So here's my dictionary, and I'll assign it to my system design group. And then when we call export, we'll see the same dictionary structure. In order to assign variables from multiple groups, we can provide a nested dictionary to the model itself. So here's a resource dictionary. And I'll point it to the resource file that I've prepared in this folder. Then I'll make that nested dictionary with the key as the group name. So here's my nested dictionary, and I'll assign it to the model itself. And then when I export, I'll see the same nested structure. So errors will be reported as PySAM errors, and potential sources include type mismatch during assignment, assigning variables that don't exist, and missing fields during simulation and other execution errors. So as an example, if I try to set something that doesn't exist or access it, it will say it has no such attribute. So now that we know how to work with inputs, let's set up that default utility scale PV project we demonstrated at the beginning. A list of available default configurations is provided in each model's page on the documentation site. where each entry is a pairing with a financial model. The set of defaults are copied from the SAM repo and will be the same as that in the latest SAM release, but may or may not be the same as the latest set being developed. So here we're looking at PV watts, and we're looking for the single owner model. So this corresponds to the default configuration called PV watt single owner. So I'll copy that and return to the Python console. Now I can use the default configurations. So here we can see that many of the input parameters have been populated. Just a few inputs are missing, such as weather resource, but once we provide a path to that file, we'll execute the simulation, set the verbosity to 1 to output any log messages. So here we see that it's completed without error. And taking a look at the model now, we can go into the outputs group and see various output types, and then extract ones that we're interested in, such as the annual energy. You may wonder, how do we run the single owner model following the PV watts model? As I showed earlier in PySAM, you reuse the same data table so that all of the input and output values from PV watts will be accessible to single owner. You may notice that with PySAM, there isn't a direct way to access that data, as it's wrapped and protected by the PySAM class with its getters and setters. Then, of course, we can't simply pass that data table from PV watts to single owner. At the moment, you have to assign the required inputs of the single owner from the outputs of PV watts. Luckily, there are usually only a few, but not catching all of them would be an easy mistake to make, so be sure to check the documentation. So I'm going to create a single owner model with the defaults configured to the same technology financial pair. I'm going to import single owner and create that default model. So you can look through the inputs and see which ones depend on results from the technology simulation. Single owner requires the energy production time series, the system capacity, and whether or not we're running lifetime simulations. So to transfer the energy generation profile from PV watts to single owner, we'll simply assign those values. So the system output gen attribute needs to be the output of the PV watts model. We also need to check that the system capacity values are equal. So that's true. And then we'll have to specify that we're not running a lifetime simulation. If we were to run lifetime simulations, we'd also have to make sure the analysis period values are the same. So a major difference between simulations in SAM and in the SDK, including PySAM and PySAM, regards dependencies between inputs. In SAM, the values for some inputs are actually calculated in the GUI to assure consistency among all the inputs. These calculations help link up dependencies among inputs in a single model, as well as dependencies among inputs in two different models. So if you modify an input that is upstream to one of these calculations, you may need to write additional code to ensure values for these inputs are correctly assigned, which is what I've done here. So now we can execute and look at some outputs, such as the PPA price. So that's in dollars or cents divided by 100. So to tie together all the pieces we've discussed so far, setting up and using PySAM, modifying models and decoding error messages, and linking sequential models, we're going to import a SAM case into Python using the code generator function. So going back to the desktop application here, I've got a PV-Watt single owner case. What we really need is just all the inputs we've defined in SAM as a JSON file. So I'm going to select JSON for inputs and save that here. So it's been exported to this JSON file with the same name as the case. Going back to PyCharm and looking at this demo script that I've written here, we've imported PV-Watts and single owner, as well as PySAM and JSON. Then we make the PySAM instance. We'll open the JSON file to load the data into dictionary and use a function to create that SSC data table that I mentioned earlier, fill it with all the PV-Watts and single owner inputs, and return that data table. We make one per model. So that's the function dict to SSC table here. And then each PySAM class is a model-specific wrapper for the SSC data structure. So to feed our already created data, PVDAT and SODAT, into our PySAM models, we'll need the function wrap, which transfers ownership to the PySAM models. So the PySAM class will automatically delete the data when it itself is deleted. So be sure to not call data free on the original data, as you would have done using PySAM directly. Then we run the PV model, transfer the required data, and then run the single owner model. And then we can run that. And then we see the annual energy and the PPA price. So that completes the section of our talk on using PySAM technology and financial models. We've covered how to create a blank, a default, and an imported model. Our final section will be about modules in the SSC library, which are not associated with the PySAM class. What kinds of functionality are included here? Some of the functionality underlying a simulation can be accessed as standalone modules. Rather than go through all the options available, I'll go through how to find these modules and how to use them. So imagine we'd like to fit PV module information found in the manufacturer data sheet to the CEC 6-parameter model. In SAM, it's this page here in the detailed model. The CEC performance model with user-entered specifications. So here we can enter the module type, the maximum power point voltage, temperature coefficients, and fit these to a model from which the IV curve can be calculated and plotted. So can we access this function from Python? If the module is a compute module, then yes. A compute module is a chunk of code that calculates results from a set of inputs. They can be combined to create a power system model, for example, combining PV watts and single owner, or run individually, like running 6-par-solve to calculate single diode PV parameters. So there are a couple ways to check if this feature is indeed a compute module. The most direct way is to look at the associated UI page, as Nick had shown earlier, but that's outside the scope of this webinar. Instead, we'll look at the SSC API, shown here, and also the SDK tool. So the list of all compute modules available in the SSC library is listed as module entry infos. There are models for solar water heating, geothermal, wind, many varieties of CSP, among other technologies. So to find the code associated with each of these compute modules, simply copy the name after CM entry and open the file with cmod underscore the name. So here it's cmod underscore 6-par-solve in the SSC folder in the SSC repo. This var info table contains the input information such as data type, a short description, the units, and whether or not it's required. A short description of the compute module can be found next to define module entry. Another way to explore available compute modules is through the SDK tool, which is automatically installed when you install SAM. We have all the available modules on the left, and you can see that the var info table information is repeated here. So once we've found the compute module name and input information that we're looking for, we can run a 6-par-solve module using a function from PySAM.pyssc. So back to my demo. The second section shows a data dictionary with technology model and financial model. The technology model I've set to 6-par-solve, whereas the financial model must be none if it's not required, as well as all the input parameters to this model, such as the cell type, the maximum power point voltage. So this function, SSC sim from dict, takes this dictionary and runs the appropriate models, and then exports the output to a dictionary. Running this script, I see that the dictionary has been populated with the output values. So I get the 6 parameters, A, IL, IO, shunt resistance, and series resistance. So note that all compute modules, which includes all the technology and financial models wrapped by SAM, can be run using this method. So in this presentation, I hope you've learned how to install PySAM, how to create, modify, and run models using a variety of methods, and how to find functionality you may be interested in from the open source code. So thank you for your time and attention. I look forward to collaborating with you.